All right, let's get started. My session today is on designing and running low-latency systems on Kubernetes. This talk is going to be kind of broken into two halves. The first half is going to be about kind of general principles for building low-latency systems and the things you need to think about and consider when you're kind of designing these architectures and actually writing the ultimate code that's going to run in these environments. And then the second half is actually on the environment itself, Kubernetes, the things that we've kind of learned running a low-latency system and the configurations you have to make, the things you need to be monitoring and understanding as you deploy these types of systems. For some background, I'm Jimmy. I co-founded a company called auth. I'm going to get a little bit more into that in the next slide. But I previously worked at companies like CoreOS and Red Hat. So I've been in the Kubernetes space basically since the beginning. I worked a lot on Kubernetes operators, kind of actually like creating that concept and teaching the Kubernetes control plane about the applications that run on top of it. Before that, I worked on container registries, and I'm actually on OCI, which is the standard for containers, defining literally the registry protocols. And then before that, I actually worked on BitTorrent standards as well. So when I was in college, I wrote some BitTorrent code, because that's what college students do. Little did I know that Facebook would actually adopt that to distribute all of the containers at Facebook across all of their servers. Be prepared for people to use your code in surprising ways is the lesson there. Cool. So low latency can mean a lot of different things. So I really wanted to clarify right off the bat, basically what types of systems we're talking about. Low latency for like a user interaction on a web page, it can be like hundreds of milliseconds, but low latency when you're doing something like financial trading or like an airplane controller is a very, very different order of magnitude. So how low are we talking today? We're talking about network services running in single-digit milliseconds. If you kind of cut out the network, you could look at it as all kind of operating with under a millisecond of latency. So I have these kind of images here. The pacemaker, we're not talking about that kind of soft or hard real-time system, but we are talking about things that could be possibly doing financial trading in the market. And kind of how that manifests itself in the kind of technologies you choose is you can actually use a garbage collected language for this type of workload, and you can run this kind of stuff in the cloud. So auth builds a database product called SpiceDB. And SpiceDB is kind of the project that has given us all of our insight that I'm going to be sharing with you so far in this deck. Basically, what SpiceDB does is it is a database, but it's optimized for storing authorization data. The reason why you do want to do this is because it gives you a lot of different workflows that are super beneficial. They basically let you model the authorization systems you have in a way that you can test completely decoupled from all of your applications. It enables your applications to query the central source of truth, where you can also then share different aspects of authorization data. So a canonical example is actually if you put a Google Drive link into an email in Gmail and you hit send, but you forget to share that, Gmail will actually warn you because it has an understanding of Google Drive's permissions, basically by using a central service internally at Google, similar to SpiceDB. And that service internally at Google is actually the inspiration for SpiceDB. Google wrote basically a paper on that, and then SpiceDB is an open source implementation of that paper. Google scale is pretty massive, and obviously this is a super critical workload because all of the requests across all of your services are going to be doing permissions checks before you can even query your relational database to get the data you're going to serve. So all this has to run correctly because if you give the wrong answer, that's a security vulnerability, but also extremely, extremely fast. Google's paper kind of cites them running at 20 million QPS. We basically tried to hit that number. We got to 1 million QPS before we ran out of IPs on Google Cloud. That's what always happens when you do these types of tests. But we managed to basically benchmark it at 5 milliseconds for the P95. This was 2-ish years ago, so we've made some massive improvements since then. But you can read more about that, the URL's here. So that kind of gives you an idea of the type of system that we designed. But how do you design these things on your own, and how do you design for the basically this target of latency for your services? I kind of jokingly say that this is all you have to do. But I think the principle behind building these systems is really to build the most understandable thing possible. So you start by writing things as simple as possible because you're battling complexity when you're fundamentally building these systems. Because the more simple something is, the more reliable it will be, the more consistent it will be in terms of its performance. And then the second step is basically to profile it. Profiling is when you sample time spent doing particular operations in your code. So you can profile different aspects of your code. For example, how much memory you're using at a particular point in time, how much CPU you're using at a particular point in time, and the real usefulness of profiles are basically it's observing the real world. So while you might write benchmarks or things like that while you're developing this code, your synthetic benchmark is not reality, but profiling is actually sampling data from reality. When you build these systems, you're going to constantly follow this loop where you are going to have an hypothesis about how you should design the system. You're going to write benchmarks. You're going to test things with those benchmarks. And then you're going to put them into production. And then you're going to observe with basically profiling tools to understand how that is performing. And only after you've proven it with that will you actually really accept that change and then move on. And you are going to follow this cycle for basically everything you do when you develop these systems. So I think there's two super critical types of profiles, and they're based around effectively lies, abstractions that a lot of programming languages and computers are giving you as a developer. The first lie, is that a CPU core can do more than one thing at a time. They can't do that. They actually are they're going to be basically doing concurrency, so they're actually going to be scheduling and swapping out the workload they do. So fundamentally, if you're trying to do multiple things at once on a single core, you are oversubscribing that core. So you're going to need a lot of tools around understanding what things are running on it, what things are the highest priority, what things are low priority, what things should be canceled. And for example, SpiceDB is written in Go. Go gives you Go routines. That's great. But if you just create Go routines without any real strategy around what is the most important thing or any logic around canceling things or setting limits, you're going to build yourself a mess. It's not going to perform well. You could have a whole bunch of low priority things completely tank the performance of a hypercritical, latency sensitive operation. The second convenient lie is that the computer has unlimited memory. So garbage collectors give you this lie. They basically just clean up after you, so you can only think about allocating. The nice thing about profiling is that you can tell where time is spent and where you're allocating. So I think you can use garbage collected language for building low latency systems as long as the language gives you the capabilities to understand where and how you're allocating, so you can work around that. The other super useful thing here is you should be able to basically tune your garbage collector based on the workload. In Go, there's really only one knob that you can tune for the garbage collector, but in languages like Java, there's many flags you can use to basically manipulate the garbage collector to work better for your workload. Cool. So in basically the spirit of the first aspect of building these systems, concurrency, the first thing you're going to do is try to parallelize absolutely everything. So SpiceDB is actually Kubernetes aware, and what it does is it actually self-clusters. So if you just deploy a deployment of SpiceDB onto a cluster, it's actually going to use the Kubernetes API and immediately auto-discover other pods running in that deployment. And then what it's going to do is it's actually going to take requests that get received by any of the pods, and it's going to break them down into sub-requests and then basically distribute that work across the cluster. The more parallel-friendly your algorithms are, the lower latency you can get things, because CPUs don't get consistently faster. They do get slightly faster every year, but really what the industry trend is, they're getting more dense. So the more parallel you can solve your problems, the lower latency everything is going to be. The other thing that you really want to use here is basically these two abstractions. They're kind of two sides of the same coin. One of them is called hedging. So hedging is when you basically duplicate the work. Because if the first guy disappears and isn't able to answer your request, you better have a backup plan, and that has to happen just as fast as if that had not failed. Hedging is really tricky, actually, because it's overloading the cluster. You're doing even more work. And so you can really hurt yourself if you're not paying very close attention to how you're doing this, and it can vary a lot. We have hedging in a couple places in SpiceDB, but there's no place where we guarantee users that hedging was going to give them better performance. It's all very much so observation-driven. On the other side of that coin, there's a thing called single flight, which is actually a function called deduplication. So this idea is if you are already serving this particular request and someone else comes in and requests that same data, when the response for the initial request comes back, you serve it to both of them. When you use this, it's incredibly powerful because everyone that asks for the same data, they get immediate responses. They get responses faster than they ever possibly could have before. So this not only deduplicates the work put onto your clusters, but also gives answers back significantly faster. We try to sprinkle this absolutely everywhere in our code. If you're not using single flight, this is definitely a library you should look into, even in probably non-latency critical workloads. Cool. So the second aspect is serving everything from memory. Basically, you're going to have to write data structures that keep as much in memory as possible if they're not already in your language ecosystem. We were lucky enough that we use a caching algorithm called TinyLFU. And the wonderful folks at dgraph actually maintain that written in Go already. So we've just been able to contribute to that project rather than having to write our own. But we have some other latency critical workloads internally at auth. And yeah, we've written our own data structures for all this stuff. So the first step is to try to get everything in memory. The second step is if you're not going to be able to serve that from memory, you better be ready to get that answer as fast as possible. So the example I give here is connection pooling. If you have to establish a connection, sometimes establishing a connection is longer than you actually can afford for your SLA. So that fundamentally, if you don't have the connection ready to go when you miss the cache, like you're going to still blow your SLA. So keeping resources like this hot and ready to be used are going to be like hypercritical to if you can't get things in memory, because not everything can be in memory all the time. The next thing is basically working with your garbage collector. In Go, you have this environment variable called Go memlimit, and this is actually what controls GC pressure. So if you do not set this variable, the Go runtime does not know how much memory is in the environment. So it might think, if you could set it to like 1 gigabyte, and you actually have 10 gigabytes available, that means when it starts to get close to 1 gigabyte, it's going to start thrashing because it thinks it needs to free a bunch of objects in memory because it thinks it's running out of memory. So you really need your environment and your processes living in that environment to be aware of each other and configured, or else they're going to do all kinds of things that you can't really explain. They just aren't logical. So the best way to actually prevent allocations and to eliminate a lot of this churn on your garbage collector is actually to reuse allocations. So if you've already made an allocation, you should be able to reuse it for the next request. The Go standard library gives you a primitive called pool, and we use this all over the place. Basically, it lets you pool the allocations, the objects that you've already allocated into one place. So you can grab one of those if there is one already available that another process has finished using. This is super, 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 this is basically the one quick hack that you can do to make anything 10 times faster if they're not aware of basically pooling allocations. You're going to do this in your libraries or programs, and then immediately you're going to realize your dependencies aren't doing this. So then you're going to provide upstream PRs to fix these libraries. And sometimes it's really difficult, but sometimes it's a really small change. And I think you get a lot of brownie points in your library ecosystem if you can make a small change to an upstream library that suddenly makes it 100 times faster. Everyone in the ecosystem will be super happy that you're kind of participating in open source then. And kind of like the last thing is, if you know how your garbage collector works, you can actually kind of save it from doing a bunch of work. For example, if you have a giant hash map in Go, and you basically don't store pointer types in it, say you just have it full of integers or basic types in whatever programming language you're using, the garbage collector can skip that whole map at once. It doesn't have to go through every individual item in the map because it knows there's no pointers, so there's nothing for it to follow. So if you have gigabytes allocated in a map in memory, you can skip all that work for the garbage collector if you just are kind of aware of tricks and things to make it so it doesn't have to check. This also has side benefits. Your CPU caches also work smarter and work way faster when you have really simple data types. So if you're doing something kind of analytical and crunching numbers, you can also get huge benefits there. Cool. So those are like super high-level principles for building the systems. Say you've got all that. Now it's time to actually run a low-latency system. So all of our products at AuthZ, they all run on Kubernetes. That's how we deliver them. I've given another talk where I kind of talk about what that architecture looks like. We've kind of been running workloads on Kubernetes since the beginning. I kind of showed you in my bio that I've been here since the beginning. So we were shocked how difficult it was to actually run these workloads optimally on Kubernetes when we started running them. And you basically have to start somewhere. So in the beginning, everyone starts with the defaults. But I feel like Kubernetes defaults are like your Linksys router defaults. They are protected. There is a password, but like it's not a really good password. But it does work, right? Like if I click on the APs on the laptop here and I see a giant list of them, I bet like half of them are going to be just the defaults that the router shipped with that people didn't change. So it is working for them. But it's kind of best effort. I have the title as, are you even trying? That's about you, it's not Kubernetes. It's like, you have not tried yet. You're just using the defaults. So by default in Kubernetes, it's going to give you no protection from any of the pods running on the node from consuming all of the resources on the pod. So if you start consuming all the memory, the Linux kernel is actually what's going to kill you. It's going to pick a random process on the machine and say, OK, like we're out of memory. I need to stop something. So that is not Kubernetes aware. That is the underlying operating system making that decision. The other thing Kubernetes will do is it will gladly put two pods of the same workload on the same node. If you are trying to run something for high availability, like you say, I need 3 of these things to run, and it puts 2 of them on the same node, and then that node disappears, you could be really hosed based on what type of software you're running. That is like a really, really big foot gun if you're running something like etcd or Zookeeper that's doing distributed consensus and needs a certain number of nodes to actually stay healthy. So yeah, the obvious thing next is, OK, how do I work with the Kubernetes scheduler? How do I give it more details to run my workloads? Our first stop here is called taints and tolerations. And this is a general concept basically called affinity and anti-affinity. And what it basically means is you're going to label the software that you are running, the pods, and then you're going to label the nodes. The software gets taints, and the nodes get tolerations. Basically, what they say are if you have this taint, you can only be run on things that have a toleration for that thing. You can use this to give yourself guarantees like only one pod of this type can run on a single node, or you can actually create a whole new work pool that is a specialized hardware configuration for a particular type of workload and prevent anything else from getting scheduled on it, and then only your workload getting scheduled onto that. This is really, really nice if you want to run specific instances for your workloads. We found that, for example, having higher core count is actually really desirable, and maybe not having hyperthreading on them is really great for low latency, but may not be great for your general purpose workloads that are things like monitoring and everything else running in your cluster. Cool. Then there's requests and limits, and this is really what everybody is going to tell you. If you say you're using the defaults, they're first going to be like, OK, here's requests and limits. This is what solves this problem. And what requests and limits are, they basically say, this particular pod, it requests this much CPU or memory to run. And then at a maximum, it has this limit of how much resources it should have before you should probably kill it because it's out of control. We're done, right? Like, that's all you have to do. Not really. So we have observed a couple of pros and cons to using this. You don't have that out-of-memory error that I was talking about before. Basically, Linux kernel isn't going to kill your process. Now Kubernetes is going to kill your process. So that at least means it's going to kill the right thing. So we made a huge improvement there. And the limits did make performance more predictable. We actually have kind of like these boundaries around our process. But actually, there's kind of like a double-edged sword here, or a double-edged blade, because when we didn't have those, we could actually burst. So if a particular thing wasn't using any of the hardware resources, we could actually burst and consume to use that. That's really nice property, but also can hurt you, because if something like a logging driver starts to burst, then that eats into your latency critical workload, and you get burnt. The other thing with these limits that I guess a lot of people don't really know is that they're reactive. So there's actually a flag on the API server for Kubernetes that says how often it polls to check that something isn't past its limits. That interval has a floor to it. So you can't make it infinite. You can't make it a millisecond. And what you see in low latency workloads, let's say you're even doing like 100 QPS, you're going to blow hundreds and hundreds of requests before this thing can react in time to actually like kill a process that's consuming all of a resource on your node. So fundamentally, it just doesn't work fast enough to be to actually solve the problem. You need something proactive rather than reactive. And finally, it doesn't really solve the problem of pods context switching or processes context switching, which, if you're not familiar with context switching, it has to kind of do with this parallelism and concurrency thing I was talking about earlier. So in parallel systems, you have probably 2 cores, and there's 2 workloads happening, and they're truly happening at the same time independently. In a concurrent system, there is actually only one thing that can be executed at a time, and what happens is you're going to actually pause execution of a particular thing, save that state, swap in a new state, and then start executing that until that gets paused, and then you swap again. This is super expensive, and what happens at those swapping points is called scheduling logic. So there's kind of 2 major ways you can choose to swap a process that you're working on. Cooperative, which is a particular event triggers it. For example, if you're writing time.sleep in your program, you don't want to sit using the CPU when you could be doing other work when you're supposed to be doing absolutely nothing for this one process. The other way of scheduling is called preemptive, which is the overall system. The scheduler gets to decide, hey, OK, you've been running for a while. I'm going to stop you and basically make sure it's fair scheduling across everybody, and everyone gets kind of an equal amount of time being ran. There's pros and cons to each of these, but the really important thing to understand about context switching and scheduling in general is that this is happening underneath you at many, many layers of your programs. The Go runtime has a scheduler for scheduling Go routines running. The Linux kernel has a scheduler for running processes on your operating system. Your hardware, your CPU, if it has hyperthreading, is scheduling different workloads across the same hardware thread as well. So there's kind of this whole hierarchy that you need to be aware of and make sure you're playing nice at every single level, or you're going to try to pick things that get rid of them altogether. Like I said earlier, if you're using hardware that doesn't have hyperthreading, you don't have to worry about the hardware one. Cool. So how do we actually address context switching in Kubernetes? Kubernetes has one last trick up its sleeve for now, which is the static CPU manager. This was introduced in Kube 1.2.6, and what it lets you do is if you specify whole number CPUs, it will actually take that and pin them to cores. There was a talk in here earlier about how to run Red Panda, and they're doing similar things here. This is absolutely basically latency and throughput are 2 sides of the same coin. So a lot of the stuff they're doing for a lot of throughput is similar to the stuff that we're doing for lower latency. But basically what we do is we pin these processes to specific cores, and then we can get guarantees that other things running on the system are not actually going to be taking away any time, CPU time from our latency critical workloads. But there is kind of one problem with this, which it's static. Like once we configure that, that's it, right? It's this many replicas and this many cores, that's it. But we can actually get back some of the dynamic aspect by using autoscaling in Kubernetes. So Amazon actually has this fantastic project, which is now no longer Amazon owned, but community ran as a part of Kubernetes SIG, called Carpenter. And Carpenter does autoscaling on demand for Kubernetes. So what happens is when you make a request to create a new replica, it will actually spin up a new machine in the underlying cloud platform. This is super, super nice because we can treat everything as static, but dynamically spin up new VMs, specifically of a particular hardware type that have the exact cores pinned to them. Basically, you have some alternatives with the other cloud providers. AKS had their own autoscaler, but actually they released Carpenter support now that it's kind of community-driven. So that's fantastic. I hope Google Cloud also does this. I would be very, very excited for everyone to consolidate autoscaling on Kubernetes. But that is the major trick for CPU pinning. If there's one thing that you take away from my talk, though, is that there's a lot of different layers and systems you have to interact with just to get something to be very consistently performing. And that, I call it the isolation model, because you have to be working basically within your own world, but purely aware of the other systems operating around you. For example, when you're trying to work in Go, or for example, the Go runtime, right? The Go garbage collector. It is in its own world. You can't really interact with it so much, but you need to play nice with it. And not only that, it needs to be aware of like the environment it's operating in. If you don't tell it, hey, we have this much memory, it's not going to be able to do the right thing. So in your code, you need to constantly be aware of the environments you're operating in, but also only touch the things that you actually have the capabilities of touching. We think that basically isolation models are super, super critical to understand, even using software. That our product documentation and our marketing actually talks about isolation models, especially in a security product like we are. Knowing that like the network boundary is completely secure is obviously also important. So we take that idea and we bring it all the way down through the whole stack, layers all the way into the code. Cool. So I wanted to thank everyone on the team that kind of did a bunch of this work for us. If you want to learn more about the Kubernetes primitives, there's this Medium URL. That's the shortest I could get it. But that will actually dive into each of the kind of Kubernetes primitives for scheduling this stuff in a way that I couldn't do in this talk. I wanted to thank KCD for hosting this event. And if you have any questions about any of this stuff, we actually have a Discord, discord.gg/SpiceDB. It's about SpiceDB primarily, but any kind of higher level questions about Go or distributed systems programming, we also answer those there. I think there's like a couple thousand people in there. And then if you're interested, we are hiring as well, always SREs, to basically run these workloads. So if this tickled your fancy, we are always hiring SREs. Cool, thanks. We have time for questions? Okay, cool. Sure.
You mentioned the Go mem limit. So in a Kubernetes context, do you want to set the memory request limits to be the same and then set the Go mem limit to equal that?
Yeah, so the question was, I mentioned Go mem limit. In Kubernetes, do you want to basically specify that and make it equal to the memory you're actually allocating to the pod? Yep, that's exactly what we do. You can use the downward API and literally specify in your manifest, like this environment variable should be set to the same value as this, which is, this is literally the request you're going to give it. So you can actually literally write that number in one place and never have to update it anywhere else.
Low-Latency mostly around CPU and some around the read part of the database.
Yep.
The database.
Yep.
So I guess you're right.
Mm-hmm.
How do you address that part while achieving consistency?
Yeah, so consistency is a tricky thing in SpiceDB. The question was, how do we, I talk a lot about the read path, but what about the write path? In SpiceDB, we actually support various backends that have different trade-offs for consistency. And one of the things that we also do is on the read path, we're also letting folks actually specify consistency at query time. So a lot of databases have like an isolation level, and that is kind of a value you probably typically set at the table level, and you set it once at the very beginning, and then you're operating in that context effectively the whole time. Yeah, you can do some tricks with how you write your SQL to get different guarantees, but effectively that's kind of the default. In SpiceDB, we actually kind of reverse that, and everything is fully consistent, linearizable by default. And we do a lot of work to do that, but obviously that's kind of slow. So then what we actually do is we we do quantization is what we call it. So we kind of round to particular timestamps and then get everyone to use those cache values. And then when you have like a read after write, you can actually say, I only need something as fresh as this particular point in time. And that way, if the cache is past that point in time, we'll give you a newer answer than maybe you needed, but it's the thing that's going to be in the cache. So you actually make those requests, or you make that consistency specification at request time. So the client, yeah, does need to be aware of it. If you do not specify anything, we're just going to use the fastest thing for the server. The fastest, yeah. So it is really tricky. You could default to the correct one, but at that point, you're probably going to get no caching whatsoever, right? Yeah, it's a trade-off. So we believe that most people can define basically their own window of like how fresh or stale something should be, and that's then a flag that they specify. So when you set up a cluster, you can say like, okay, by default, I want it to be like maybe 1 second, or maybe I have a slower thing, so it can be 30 seconds, right, for the window at which we're rounding. So we kind of give people enough configuration that they can build kind of like the environment where the defaults make sense to them.
Shared between all running pods?
That is the configuration across the whole cluster, yeah.
No, the caching is shared across all.
Yes, yeah, that caching is then all the pods. Yeah, cool. I think we're out of time, but thanks everyone.